welcome back to our nano-analytics lab. I am Chiara Labanti, and today I would like to share with you some of our results on the molecular engineering of small molecule donors for efficient organic photodetectors. So, first of all, what is a photodetector? We find them in a wide variety of applications in our daily life, and mostly they are based on silicon, but we can easily substitute silicon with organic materials, which are much better for lightweight, colorful, and flexible application. So now we can find organic photodetectors in a very broad range of examples, such as position sensors, optical communication, full color imagers, and even advanced biomedical applications. And today I am going to talk about this type of devices made by Samsung. So these are basically state-of-the-art co-evaporated organic photodetectors. So these are based on a bulk heterojunction, so a blend, vacuum deposited blend of a donor and the acceptor material. And we want to extract electrons produced upon light excitation on these devices by the interfacial electronic offset between the donor and the acceptor materials in the blend. And here we are using fullerene as an acceptor and different types of small molecule as donor material. So we want to understand what is the role of the molecular, the design of the molecular structure of these small molecule donors. So first of all, we need to characterize how these devices are working. So one of the important figures of merit to check to understand the performance of our photodetectors is the photodetection speed. And in a machine like this, we can check the transient of the photocurrent and see how fast the on and off dynamics are. So it's very interesting to see that highlight, when we operate our devices in higher illumination, higher intensity of illumination, the planar molecule has better performance, so faster photocurrent transient like here, and this is due to a smaller presence of shallow traps, so better order, energetic order at the end edge. But on the contrary, when we operate in low light with weaker illumination, the situation is reversed. So here we see that the planar molecule has slower off and on ratio in the weak illumination, and this is due to the additional presence of deep traps that would be totally filled in high light, but they only affect the performance in low light. So we now want to understand the origin of these trap states in terms of detailed material characterization, so we need to move to another lab. So now we are back in our nano-analysis, the central part of our lab. We already found the main pieces of equipment here in this lab tour made by my colleague, and now we want to use our machine, the Raman system, to investigate the properties of this material. So first of all, from here we can also extract some information on the photoluminescence emission, and we can see very clearly that the planar molecule has very strong signs of aggregation. So in the neat material we have very broad and intense photoluminescence, which we attribute to intermolecular states, so very strong aggregation. And when we blend with the fullerene, we are basically destructing this aggregate, and we have dominant emission from the interfacial states, but we still preserve some degree of aggregation, so we still have some leftover emission from the aggregate. So to confirm this effect, this very peculiar morphology, we can use the Raman spectrum for, of course, investigating the vibrational modes of the molecules. And we can see that the effect of blending for the twisted molecule is very localized, just on specific modes, but for the planar molecule is very general, so all the modes are affected by the blending. So again, we think this is compatible with some stronger organization of the morphology. But also, we need to consider the second factor, which is the potential creation of chemical compounds with the fullerene. So for the planar molecule, we can have this reaction, and the Raman spectra of the adduct, the complex with the fullerene, are partially compatible with what we actually observe in the Raman spectrum of the blend. So we think there is both the aggregate presence and the presence of adduct. So now we want to understand if this has an impact on the energy level and the trap state, and so we need to move to the energetic characterization. Okay, so now we move to our APS system, so the system to detect study the energy levels of the materials by photoemission. And basically we can see that first of all the cutoff of this photoemission is much sharper for the planar molecule. So this is an indication of a better energy order, and so lower presence of shallow traps, which affect the high light performance, as we saw before. And the second observation is that when we blend these materials, in both cases we are shifting deeper the energy levels. But this shift is much stronger for the planar molecule. So we think that originally in the lead material, the planar molecule, due to the aggregation, has quite shallow energy levels. And then when we blend with the fullerene, we are disrupting this aggregation, and we are shifting down the majority of the states, shifting deeper, but the residual aggregate state will be present quite deep into the band gap. So this would create a possible origin for trap states, deep trap states. And the second thing to consider is the adduct formation. So also the complex with the fullerene, the adduct would be present quite deep into the band gap. And these two, the aggregation and the adduct formation, would act as deep traps and affect the performance in low light. So from this work, we can give some interesting design guidelines for small molecule donors for organic photodetectors. And we understood that twisted morphology, twisted geometry, is not very good in high light due to higher presence of shallow traps, but the performance is quite insensitive to the light intensity, so we can go down to low light. On the contrary, planar molecule is very good in high light due to better energetic order, lower presence of shallow traps, but the planarity also induces some aggregation and also reaction with fullerene, which can act as deep trap in low light. So we always need to bear in mind the target application of our devices when we design candidates for small molecule donors. And so to conclude, I would like to leave you with this beautiful vision of the Royal Harvard Hall, and I would like to address you to our